I'm just gonna start recording. All right. So functions and model. Today we're going to focus on exponential function. Do you remember what exponential function is? We say some number raised to the power x. That's exponential function. Look at the definition. So we say a to the power x. So the x there is actually the exponent. All right. So please don't get confused between a power function and an exponential function. A power function, you have x being your base and some number being the power. For an exponential function, on the other hand, you have a number being the base and x is actually the exponent. All right. And if they give you something like a to the power n, so if they give you stuff like this is just the same as saying that multiply a n times. All right. So a times a n times. For example, if I say a to the power of 3, obviously this is just the same as saying a times a times a. All right. So that's basically what it means. Okay, now what happens when the exponent x is equal to minus n? Right? You see, minus n, we treat it as a reciprocal. So I'll show you just now. Just want to change this color. So if you have a to the minus n, the minus there means reciprocal. So it's 1 over a to the power n. All right. Now what happens when that exponent x is a rational function? Remember, a rational function by definition is p over q, where p and q are integers and q, in this case, we want it to be greater than 0. All right. So in that case, you have a to the power p over q. Now look at this carefully. A to the power p over q means the cubed root of a to the power p. All right, or you can say the cube root of a all raised to the power p. I'll do a little demonstration now. So let's say, for example, I give you 2 to the power, let's say 5. Let's say 5 over 2. All right. So if I give you 2 to the power 5 over 2, you start with a 2 there at the bottom. The 2 at the bottom means square root. So you have square root of 2. So you're going to end up having square root of 2. And then you need to say all raised to the power 5. All right. Square root of 2 raised to the power 5. And now the big question is, what now happens if that variable is actually an irrational number? For example, root of 3, 2 to the power root of 3, or 5 to the power pi. Now, if you notice the root of 3 and pi, they're irrational numbers. And by definition, we say irrational numbers, they have non-repeating decimals. All right, that's just the easiest definition. Now, if I plot the graph y equals to 2 to the power x, where x is rational, notice it, you get a sketch that looks like this. And if you notice it, there's some holes there, all right? Because now I'm saying that I just need x to be rational. But you agree that if you consider x to be an element of real number, it means you're going to have both rational and irrational number. Because the irrational piece is missing, that's why in this case you see the holes. So it's the dots and the gaps in between. Now those gaps in between is just the value of your function when x is actually irrational, all right? So for you to get a solid sketch, you will have to sketch x element of real number, not just x being rational. Right. Now let's look at this. So we know root of 3 typically lies between 1.7 and 1.8. Now if I erase everything, so if I say 2 raised to the power 1.7, 2 raised to the power of 3, notice the inequality sign does not change. Why? Because my base 2 is a positive number. All right. Now we know exactly what 2 to the power 1.7 and 2 to the power 1.8 mean. Because you know that this number, the 1.7 and 1.8, they're rational numbers. Remember, rational numbers, we say you have non-repeating root. 1.7 is just the same as 17 divided by what? I'm sure someone is thinking about it. You just divide that by 10. All right. So 17 over 10 is just a rational number. All right. Now let's look at further analysis. So we've established that to two decimal places, root 3 still lies between 1.73 and 1.74. If I keep increasing the decimal places, you see what's happening, and it can go on forever. And if you raise everything, so if you say 2 raised to both sides, again the unequal sign does not change. All right. So the best way to approximate this guy there will be to look at these two endpoints there. All right. Now it can be shown that there is exactly one number that is greater than all of these numbers. All right. So if you're doubting where these numbers are coming from the previous slide, so they're talking about all these numbers here. So it's greater than all of this number, and then it's also less than all of these numbers. This is exactly one number, and we know what that number is. It's 2 to the power root of 3. All right. So that's what they mention here. All right. So we define 2 to the power of 3 to be this number, and then using the preceding approximation process, we can compute it correct to 6 decimal places. All right. So if you compute it to 6 decimal places, you get something that looks like this. All right. Now, look at what happens. So initially, I started with the sketch of y equals to 2 to the power x, and I specified that x is only rational. And I had a sketch with dots, all right, with holes, basically, because they're missing values. I'm only focusing on rational numbers. Now, if I say x is a real number, it means I'm considering both rational and irrational numbers. Now, what do I get? I get a solid sketch, all right, with no holes. All right. So please know what the difference is. Okay, those are some sketch for the exponential function. So the first you need to notice is when the base is bigger than 1, notice it, you get an increasing function. But look at this, when the base lies between 0 and 1, so a fraction, you have more or less a decaying curve. This is going the opposite direction. All right. Now, let's look at these three cases. The first is you have an exponential function a to the power x, where a lies between 0 and 1. We've already seen that. That is a decaying curve. You can see it's decaying. And where does it cut the y-axis? It cut the y-axis at the point 0, 1. So when x is 0, a raised to the power 0 is 1. So any number raised to the power 0 is 1, except 0. All right. So in that case, it cuts the y-axis at the point 0, 1. Now, when a is equals to 1, so in this case, you just have 1 to the power x, and 1 to the power x is just 1, all right? 1 raised to any number is 1, so you see, you just have this horizontal line here, straight horizontal line. Now, what happens when a is greater than 1? So when the base is bigger than 1, you have a growth curve, so this one grows exponentially, all right? So see what the difference is between these two. So the one, a lies between 0 and 1, we see it's a decaying curve. When a is greater than 1, we see it's growing exponentially, and when a equals to 1, it's just a straight line. Some laws of exponential function. Guys, you need to remember these laws for your test. The first law says that a to the power x plus y, I can write it as a to the power x times a to the power y. I'm sure you've seen this from high school. If you multiply two numbers with the same base, you add the power. That's what they're simply saying. If you divide in two numbers with the same base, or two exponents with the same base, you just subtract the power. And then this one, if you have an exponent raised to some power y, you just need to multiply those powers, the xy. Then this one is more of a distribution law. So if you have a times b, all raised to the power x, you can distribute that power of x to be a to the x times b to the x. All right. For example, if I give you, let's say for argument's sake, 2b, and then I say raised to the power 2. Now, the first you need to notice is using property 4, each of these needs to take that power. So I have 2 to the power 2, which is 4. And then I have b to the power 2, which is just b squared. All right. So guys, please make sure that you understand stuff like that. The trick here is that the power 2 is applied to a bracket. So this whole thing is inside the bracket. It means everything inside this bracket needs to get that power. Now, if I change things around, I say 2b to the power 2. Now, this is completely, so these two are not the same, guys. These two statements, they not the same. All right, so they're completely different. These two are not the same. Why? Because the first one, the power 2 is only associated with b. So this 2 there is just a constant. All right. But for the second case, there is a bracket. It means everything inside that bracket must get that power. Hope you're going to remember this. All right. Now they ask us to sketch the graph of the function y equals to 3 minus 2 to the power x and determine the domain and the range. All right. Usually the way I ask it, I will say that use transformation to sketch the graph y equals to 3 minus 2x. So it's a nice question I can actually ask you. So how do you do it? You start with the parent function. You notice that the parent function there is 2 to the power x. And it's easy to sketch. The base is 2, meaning that it's bigger than 1. Therefore, it is a function that is growing exponentially. And where does it cut the y-axis? It cut the y-axis at the point 0, 1. You can see that. So it's easy to sketch the parent function. Now the next you need to see, you need to negate it. So there's a negative there. So we need to now we need to sketch this guy there. Y equals to minus 2 to the power x. What does minus in front of this mean? It means reflection about the x-axis. So if it's up there and I reflect it about the x-axis, it's now down here. All right. It now goes down there. All right. There we go. Reflection. We're not done because there's still a 3. We need to do with this 3. Now, 3 simply means you shifting 3 units upward. I'm going to show you in the next slide. So you see what 3 does. 3 simply means shift the graph 3 units upward. And your asymptote is going to change. If you remember where your exponential function cannot be equal to 0. When I say cannot be equal to 0, a to the power x can never be equal to 0. Any number a to the power x cannot be 0. So in that case, the x-axis initially acted as your asymptote, or your horizontal asymptote. So when you shift it 3 units up, it means y equals to 3 now becomes your new asymptote. It means that graph will not cut. It will not traverse that line y equals to 3. All right. And if you notice it, now you cutting at a different point there. For example, if I say let x be 0, 2 to the power 0 here is going to be 1. 3 minus 1 is 2. You see, now you're cutting at 0, 2. It's no longer 0, 1. Okay, what is the domain? Guys, if I ask you my test domain, right, especially for a sketch, for a graph, domain means you look in the x direction. Domain, what are the possible x values that satisfy my function? You can see the graph goes all the way to minus infinity, and it goes all the way to positive infinity. Therefore, we just say a set of real numbers. For minus infinity to infinity means your domain is just the set of real numbers. For range, we're not looking in this direction. So we're looking at what are the possible outputs that you can get. So we're focusing on y now, the output. Now, if you notice it, there's a restriction. Down here, the graph goes all the way to minus infinity. But there on top, it cannot cut that line there y equals to 3. So you see, it has to stop at 3. All right. The reason why we're not including the 3 is because if you try to set y equals to 3 here, you're going to have that 2 to the power x equals to 0, which is not true. Like I said, your exponential function, a to the power x cannot be equals to 0. That's why we exclude the 3 itself. Now, why do we need the number e? If you notice it, if I give you the graph y equals to 2 to the power x, y equals to 3 to the power x, I can get the slope at the point 0, 1. All right. If you compute the slope for the first one, notice that you have something like 0.7 approximately. If you compute the slope at the point 0, 1 for this function y equals 3 to the power x, you get approximately 1.1. You see, those are decimal values. We don't want to use decimal values because for our calculus course, we say students are not allowed to use a calculator, so I'm not expecting to see decimals. So to make life easy for us, we want to focus on a graph where the slope will give us some value that has no decimal. All right. So here, what they're simply saying is we can approximate the slope for 2 to the power x. We can approximate the slope for 3 to the power x. But again, the decimal values, all right? So it makes our life really difficult because we have to deal with decimal. Now, look at the cool thing about using your base to be e. Well, if you use your base to be e, the slope at the point 0, 1 is equals to 1, exactly 1. You see, no decimal. Right. So we say some formulas of calculus is greatly simplified just by you adjusting this base here to now becoming the base e. So it becomes e to the power x. So it makes computation very easy. Hence, that's why we're interested in our base being the number e. All right. And we say that such number of interest is denoted by the letter e. You can see that it was first chosen by a Swiss mathematician, and yet they say because probably the first letter of the word exponent is actually an e, so he thought maybe e is a very important number. All right. E itself is approximately equal to 2.71828, but like I said, you're not allowed to use a calculator, so if you compute and you have e in your final answer, just leave it as e. All right. And now if you notice it, this number 2.71828, it lies between 2 and 3, right? It means that the graph of e to the power x will also lie in between 2 to the power x and 3 to the power x. There you go. You see the red graph in between there. That's the graph of e. It lies in between the two graphs. And we call this a natural exponential function. It's very important in calculus because it makes our computation easier and faster. Okay, now I say graph this function. I'll just add an extra word in there to say use transformation, because that's how I normally ask it. Use transformation to sketch this function, this exponential function. And as usual, I say state the domain and the range. When I use the word state, it means you don't need to show me anywhere. I can just write the domain and the range. All right, just state it. Now, how do you sketch this using transformation? You start with the parent curve, which is y equals to e to the power x. We know e is 2.71, so it's bigger than 1. Therefore, you expect a graph that is growing exponentially. Now, if you notice it, I'm replacing x with a minus x. And in transformation, this is called a reflection. All right, reflection about the y-axis. So now, instead of growing exponentially, it's going to look like it is decaying exponentially. All right, so you're going to have something like that. Now we left with what? There's a half in front here. What does this half in front here means? The half there means shrinking. You're shrinking vertically. All right, shrinking, vertical shrink. We did that in the previous class where we discussed vertical and horizontal shrinking and stretching. All right, so make sure you study. Let's see what the half does. So the half basically shrink the graph. I know it's hard to see because you just shrink it vertically. And then the last step is the minus 1. Minus 1 now, what it does is to move it 1 unit downward. See what happens? Initially, your x-axis was your asymptote, meaning that the graph could not traverse the x-axis. If you move it 1 unit downward, it means y equals to minus 1 now becomes your new horizontal asymptote. So that graph again cannot cut that line y equals to minus 1. And notice it now it's going to pass through a certain point there. How do you know what that point is? Ask yourself what happened when y equals to 0. All right. So to know what that point is, you just need to set y equals to 0. We call that the x-intercept. And very important, I know this sketch here looks almost like this sketch. I'll show you quickly. It looks like this one, but there is a difference. I'll show you what the difference is. The difference, to prove to me that you've actually done the shrinking, because some people do cram work or the copy from some website, and they will just sketch this without noticing that there's a difference. Now the shrinking has occurred. Notice it. It now cuts the y-axis at 0.5, not 0.1. You see. So I'm going to check for stuff like this, those little details, to show that you've actually done the shrinking. Why is this 0.5? Come to this function here. What happens when x equals to 0? You have half times e to the power 0, which is just half times 1, which is half. Therefore, the point of intercept there, where it intercepts the y-axis, is going to be 0.5 to prove that you've done the shrinking. Okay, let's discuss the range and domain. Domain, again, notice it goes all the way to minus infinity. In this direction, it goes all the way to plus infinity. Therefore, it's a set of real numbers. And then for the range, obviously, we're looking in this direction. We already know that it can't cut that line y equals to minus 1. So it's going to be from minus 1 all the way to infinity. All right, go practice, guys. Let's look at inverse functions and logarithm. Now you need to pay more attention. Now, what's the difference between those two functions that you see on my right here, f and g? So f and g, think about a to be some input value and b to be some output that comes out from the function, from each of those functions. Let's start by analyzing the function f. So for f, if you notice it, I put in 1, 2, 3, 4, and f spits out 2, 4, 7, and 10. Notice it, every input gives a unique output. All right, so unique input gives unique output. Now look at the function g. There's a little bit of a difference. You have two inputs that give us the same output. All right, there is an explanation for this. We call this a violation of one-to-one rule. All right, so our first function f is a one-to-one function. When we use the word one-to-one, it means for every input, every unique input gives a unique output. It means no two inputs can give you the same output. We call that one-to-one. But g is not a one-to-one function because I have two inputs, so I have more than one input that gives me exactly the same output. All right. The best example there to test is, let's say, a function that is not one-to-one. Let's say y equals to x squared. Y equals to x squared. All right. Y equals to x squared. Now answer the question. What happens when x equals to 1? You get y equals to 1 squared, which is 1. What happens when x is minus 1? Again, you get 1. You see, clearly, the graph y equals to x squared is not one-to-one. But I'm going to show you guys an easier method in case I ask you my test. Is this function one-to-one or not? How I expect you to answer. Let's see how you're supposed to answer. Okay, it's coming the next slide. So now let's go over the definition for one-to-one function. They say function f is called one-to-one if it never takes on the same value twice. So for f of x1 not equals to f of x2, this happens whenever x1 is not equals to x2. So if x1 is not the same as x2, therefore f of x1 must not be equals to f of x2. I hope that makes sense. All right, and this is how you're going to prove if something is one-to-one, especially if it's a nice graph like what we saw before, y equals to x squared. We call it the horizontal line test. Guys, you need to remember this horizontal line test. Before I proceed, I would remind you of what the difference is between vertical line test and horizontal line test. I know most of you are now confused. We saw vertical line test, now we're talking horizontal line test. What's the difference? Vertical line test is just to see if a certain curve we have is a graph of a function. All right. Horizontal line test, on the other hand, is to test if a function is one-to-one. I'll demonstrate both of them side by side. Let's start with, let's say I have a function that looks like that. Let's start with vertical line test. So vertical line test says, is this curve the graph of a function? Now, if I draw a vertical line, let me just change the color. So if I draw a vertical line here, notice it intersects twice. Because it intersects twice, we say this is not the graph of a function. It is not the graph of a function. So this curve is not the graph of a function. Or in simple terms, we say that this is not a function. All right. Now, let's discuss horizontal line test now. We want to see if this is one-to-one. So one-to-one, again, I'll just change the color just so that we can see them differently. So for horizontal line test, notice it. It doesn't matter what horizontal line I draw, it would always intersect at exactly one point. All right. So there's two things that we can see here. First thing is this curve that is being drawn here is not the graph of a function because it fails the vertical line test. However, it passes the horizontal line test, showing that it is a one-to-one function. I'm sure you're going to now ask me, but when is a function not one-to-one? Let's do this. Let's say a function that is not one-to-one. Y equals to x squared graph. Is this one-to-one? The answer is no. I'll show you now. Now, if I draw a horizontal line, see what happens. I intersect twice. Once you intersect twice, it means that that function is not one-to-one. So in my test, if I say, is this function a one-to-one function? You can choose to sketch, do a rough sketch, and then draw a horizontal line, and then tell me that it intersects only once, therefore it's a one-to-one, or intersects more than once, therefore it is not one-to-one. If the curve is too difficult to draw, I'll show you guys another technique. You can use the idea that if you have f of a, if you have f of a equals to f of b, for example, and if you simplify both sides, so substitute a in your function, substitute b in your function, simplify both sides, you should end up with the conclusion that a is equal to b. So this is the most general method that you're going to use to show that a function is one-to-one. I mean, that is if you can actually sketch the function. I mean, the function is very complicated that you can actually sketch it. Just say f of a equals to f of b, simplify left and right hand side, see that you come to the conclusion that a equals to b. All right. For example, let's apply this general formula to a function that is not one-to-one so that you see that it works. So let's use y equals to x squared. If I say f of a, my left hand side is going to be a squared. Everyone is happy. And then my right hand side, if I say f of b and I'm putting in y equals to x squared, I'm going to have b squared. Now, if you notice it, if I try to make any of them the subject, a is going to be equals to plus or minus b actually. So you see, because there's this doubt here, this plus or minus piece here, it means that it is not one-to-one. All right, there you go. I hope everyone is happy with one-to-one. I hope in your test everyone will be comfortable. All right, let's look at the function as one-to-one. F of x equals to x cubed. F of x equals to x cubed. Look at this. If I draw any horizontal line, it will always intersect exactly once. Conclusion, it is one-to-one. If you're not comfortable with this method, please just use the one that I showed you earlier. F of a equals to f of b. Come to the conclusion that a is equals to b. All right, let's look at inverse function. Now, why is one-to-one function important? Because now someone is going to ask themselves, but why are we spending the whole day talking about one-to-one function? Why is it important? A function has an inverse only if it is one-to-one. So it is so important for a function to be one-to-one so that it can have an inverse. So no one-to-one means no inverse. All right. So if I give a function that say find the inverse, if you're smart enough to spot that it's not one-to-one, then just conclude that there is no inverse. All right. Because if you try to find the inverse, you notice it's not going to work. It's as easy as that. All right. So they say let f be a one-to-one function with domain A and range B. They say then the inverse is denoted as f to the minus. So this minus one here means inverse, guys, not reciprocal. All right, there's a whole slide that explains that issue there of reciprocal and inverse. So the inverse has domain B and range A. All right, and it's defined by f inverse of y equals to x. This is true, and it implies that f of x is equals to y. All right. I would, okay, um, this this page here is showing you what F inverse actually does. They say F inverse is just undoing what F does. It's like the reverse process. Assuming that you push in your trolley, inverse, Mr. Inverse will be the guy that is pushing your trolley in the opposite direction. So he's trying to stop your trolley from actually going. So, for example, look at what F is doing. F maps some value x to some output y. F inverse is doing the reverse process, taking it from y back to x. So it's reversing the whole effect. Guys, this is so important here. The domain of your inverse function is the same as the range of your original function. And the range of your inverse function is the same as the domain of your function. In other words, if I ask you what is the domain of your inverse function, guys, if you can compute the range of your original function, you're done. So if I ask you to find domain of inverse function, you don't have to go all the steps to find inverse function and find the domain. You can just find the range of the original function and you're done. All right. So please remember this table. All right. All right. Now, here they say you need to be very cautious, guys. It happens every year. I mean, I don't know how many years I've been at usual, but this mistake we see it every year. There is a difference between reciprocal and inverse. I'm going to explain now. F minus 1x, so f to some power minus 1x. This means inverse. So if it's inverse, you see me doing this. I'll write the minus 1 here in between. So if I do this, it's inverse. All right. This means inverse. Some people say reciprocal. This is 1 over f of x. I've seen that so many times when I'm acting. All right. If it's reciprocal, we're going to write it in this form. It will be f of x. I put it in bracket and I say all raised to the power minus 1. This one means reciprocal. This one means inverse. Guys, please know what the difference is. So many times my test I say find the inverse. Someone just gives me the reciprocal and get a 0. That is disturbing, guys. I've seen that every year. All right. So I hope this year is going to be the year with difference. All right. Let's see if we can do some nice examples. So here we just need to find inverse function. It's fairly easy. Why? I'm going to show you now. They give you f of 1 is 5, f of 3 is 7, f of 8 is minus 10. Then they say find f inverse of 7. Now f inverse of 7, you come here. If f of 3 is 7, therefore f inverse of 7 was 3. Remember what that previous diagram was doing. F inverse was reversing the process. If I put in 3, I get 7. Therefore, f inverse of 7 means when I put in 7, I'm going to get 3. All right. It's going the opposite way. So f inverse of 7 is 3. Similarly, f inverse of 5 is going to be 1. Why? Because f of 1 is 5. And f inverse of minus 10 is just 8. Why? Because f of 8 is actually minus 10. It was given here. You see, this is easy. Inverse, reverse is the whole process. All right. This is just another sketch to show you what inverse is doing. I think there's so many examples now to show you what the f inverse is doing. F maps elements from A to B. F inverse instead maps stuff in the opposite direction from B to A. All right. Let's discuss something called cancellation law. Okay, before we get to cancellation law, please look at definition 3 there. It says f inverse of x is equals to y. Remember, bidirectional means if and only if. I'm sure you guys, you remember this when we did logic, all right? Bidirectional means if and only if. All right, so f inverse of x is equals to y if and only if f of y is equals to x. All right, now how does the cancellation law work? If I give you f inverse of f of x, you just get x. All right, for every x in A. And then here, f of f inverse of x. Again, you're still going to get x. All right. For example, if I give you, let's use cos instead. Let's say I give you cos inverse of cos anything. Let's say cos of, I'll just say x. All right. Now cancellation law applies, right? Cos inverse of cos of x, you know you're going to get x. All right. So it's the same idea. Sine inverse of sine of something is just that 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 thing itself. All right. Again, this diagram is just showing you what f inverse is doing. I don't know how many diagrams we have here, just to make everyone understand what f inverse is doing. I have some input x, it goes to my function f, I have f of x as output. What the inverse does is it just gives me back my x. So if I apply f inverse to my original function, I just get x, which is what I started with originally. All right. So we say f inverse undoes what f does. How do you find the inverse of a function? It's a must know, guys. You must know how to do this. It's a must. All right. First step is write it in the form y equals to f of x. I'll just skip this step here. Just follow my steps. Second step will be swap x and y. And then the next step, just make y the subject. I'm going to show you using an example. There's 3 steps involved. First step, write it as y equals to f of x. Step 1. Step 2, swap x and y. Means where you see x, write it as y. Where you see y, write it as x. That's step 2, swap x and y. And then the next step is just solve for x. Now, if you make x a subject there, you get cupid. All right, if you make x a subject, you get cupid. Therefore, you say f inverse of x is just equals to this. All right. Guys, practice. There's so many examples in the textbook. How do you sketch the inverse function? If I actually in a test, I give you a function, I say, give me the sketch of the inverse function. It simply means you just need to reflect the original function along the line y equals to x. All right. That's what the sketch of the inverse function. So I have my original function. If I reflect it along this line y equals to x, what do I get on the other side? The inverse function, the sketch of the inverse function. All right. Let's try another example. Let's assume that my original function is this guy here. And I ask you, what is the sketch of the inverse function? If you reflect that along y equals to x, notice it's going to be somewhere there. That will be the sketch of your inverse function. I hope everyone is happy. This is another example. So you have your original sketch is this blue one here. So if you sketch this root, you get this piece here. And if you reflect along y equals to x, you have your inverse sketch, which is now this one here. All right. Logarithmic function. All right, logarithmic function. I'll go straight to definition 6. Now, if we give you log x, you see the a there you see is the base. All right, and so we say log of x to the base of a is equals to y if and only if a to the power y is equals to x. Guys, you need to remember this definition. So log x to the base of a equals to y. It means that a to the power y equals to x. For example, if I say that log of, I'll just use x, is equal to, let's say 2, for example. Now, if you notice it with my log, I didn't specify what the base is. If I don't specify the base, it means the base is 10. If the base is not 10, then I'm going to mention what that base is. And very important, the base has to be positive and it cannot be equal to 1. All right. So your base needs to be greater than 0 and it must not be equal to 1. All right. Very, very important. So you can have a negative base or a 0 base, all right, or a base of 1. So in this case, you're going to have that x is equals to, if I have to apply definition 6, we're going to see that x is going to be equal to 10 to the power 2. All right, 10 to the power 2. So I just apply definition 60. Cancellation law. All right. Log of a to the power x to the base of a is equals to x for every x element of a number. All right. The trick here is if you apply the laws of logarithm, you can take the power in front of the log. All right. There's a rule of logarithm that says log of any number to the same base is equals to 1. So log of any number a to the same base a, this has to be equals to 1. Now, if you apply this rule, if you take this x there, you transpose, so you take it in front of the log, you have x times log of a to the base of a is just the same as x times 1. That's why we have x there. Hope everyone is happy. And we say for every x element of a number. Now, the second one is also very important. A raised to the power log of x to the base of a, you also have x. So, for example, if I have 2 and I say raised to the power log of any function, let's say log of x, and then I say base of 2. So if you take 2 raised to the power log of the same base 2, therefore your output is just going to be x. It's just equals to x. That's how the cancellation works. And why is x has to be greater than 0? Because there's no log of 0 or log of a negative number. All right. So x has to be greater than 0. Keep in mind, log of 0 is undefined and log of negative number is undefined. And those are just some graphs of log function. Properties of logarithm, guys, go practice this. If x and y are positive numbers, then remember we're mentioning the fact that they are positive numbers because we don't want if any of them is negative, is going to affect our logarithm log. There's no log of a negative number, so they have to be positive number. So log of xy is the same as log of x plus log of y. When I'm subtracting 2 log, it's the same as dividing x over y. And remember, I mentioned this in the previous slide. You can take this power, the arrow in front of the log. So log of x to the power arrow to the base of a is the same as arrow times log of x to the base of a. Arrow, there can be any real number. That's some example. What is log of 80? You see the bases, they are the same. So log of 80 base 2 minus log of 5 base 2. We say that when we're subtracting 2 log with the same base, what do? You divide. So 80 divided by 5 is 16. How do I get to 4? We can write 16 as 2 to the power 4. Why are we writing it as 2 to the power 4? Because we're trying to use that idea that log of any number to the same base is equal to 1. So if I have log of 2 to the power 4, I can take this 4 in front of the log, and I have 4 times log of 2 base 2, which is just 4 times 1, which is equal to 4. All right. Natural log. Natural log is denoted by ln, so we use the word ln. So when you see ln, guys, is logarithm. It's just a natural log version. All right. So natural log, the base is always e. So whenever we talk of natural logarithm, you think of your normal log, but this time with the base being equal to e. All right. You can see what the definition is. Ln of x just means log of x to the base of e. Ln of x equals to y. Ln of x is equal to y if and only if e to the power y equals to x. All right. Ln of e to the power x is equal to x. Why? Because ln itself is log to the base of e. And we can use that rule that says I can take x in front of the log, and I end up with x times log of e to the base of e, which is 1. So x times 1 is x. Cancellation rule, guys, remember this. I mentioned this second one already. E raised to the power ln of x is the same as e raised to the power log of x to the base of e. Cancellation rule still applies, and x then needs to be greater than 0. Why? Because there's no ln of 0 or of a negative number. Remember, ln is log. There's no log of 0 or a negative number. What happened when x equals to 1? Ln of e is equals to 1. Why? Because ln of is log of e to the base of e. All right. Okay, they say find x if ln of x equals to 5. So ln of x equals to 5 means that e to the power 5 is just equals to x. So x is just e to the power 5. This one is very straightforward and easy. They're just explaining how we got the change of basis. All right. So I can convert my logarithm from a certain base to a new base using this idea. All right. So the trick here is, I will show you. So log of x to the base of a, I want to do change of base to base of e. So I'll start by saying that it's the same as log of x to the base of e, which we call ln of x, divided by log of a to the base of e, which is called ln of a. I'm sure some of you are getting confused. Let me do a different example. Suppose I want to do change of bases from base of 2 to base of 7. How do I do that? To change this to base of 7, I'm going to say the log of 5 to base of 7. So I have log of 5 base of 7. At the bottom, I'm going to say log of 2 to the base of 7. All right, I hope everyone is happy. That's how we do change of bases. So change of bases, you take log of this number here to that new base that you want, divided by log of the old base divided to the new base, all right, that you want. All right, that's how we do change of bases. And take note, change of bases is usually important. They say evaluate this correct to 6 decimal places. Log of 5 to the base of 8. Some calculators don't allow you to change the base for your log. So for you to use those kind of um, okay, I won't say anything about people who have those kind of calculators. For you to use those kind of calculators, that doesn't allow you to insert a different base other than base of 10. You can choose to do change of bases to base of e, which we call ln, right? So log of 5 base of 8 is the same as ln of 5 over ln of 8, and every calculator has ln, so you can quickly punch ln of 8 over ln of 5 over ln of 8 and give me to 6 as well. Obviously, you know already this is not a question I can answer in my test because you're not allowed to give me decimal as an answer or even use a calculator. All right, those are some sketch. So they say we have to sketch. Again, we're using transformations to sketch ln x minus 2 minus 1. So the parent curve there is just ln of x graph. Guys, this is how the ln function looks like. And then what minus 2 does is it means you need to shift this function 2 units to the right. All right, initially you cut there at 1, so now you're going to cut at 3. You can see that we're cutting at 3. And the y-axis was your vertical asymptote. Now the line x equals to 2 is going to be your new vertical asymptote. Finally, what does minus 1 mean? It means shift your entire function 1 unit downward. That is what happens there. All right, we shifted 1 unit downward. You see, we move from the point 30 to the point 3 minus 1 because we've shifted 1 unit downward. Go practice again in preparation for your test. All right, let's look at inverse trigonometric functions. Pay attention, guys. Sine function on its own does not have an inverse, right? Because look at this case here. It fails the horizontal line test. It is not one-to-one. Because it fails the horizontal line test, it means looking at this case here, we say that there's no inverse. However, there is a way for us to compute the inverse. If we restrict the domain, the idea is to restrict the domain. Now, if I cut a piece of the sine function from minus pi over 2 to pi over 2, yes, now I get a function that is one-to-one. You see, now I have a function that is one-to-one and it actually has an inverse. All right. And by the way, that is a sketch. You need to learn how to sketch this inverse function, guys. Just know how to sketch it. All right. All right. So we're just showing you what happened. We move from something that fails the horizontal line test is not one-to-one. We made a plan. And what was our plan? To restrict the domain. So we cut a piece of this. So we cut it from minus pi over 2 to pi over 2, which is what you see here. And now this function um, passes the horizontal line test, meaning that it's one-to-one. Therefore, you can get the inverse, all right? There you see where we define sine inverse, we always mention that there's a restriction. It's from minus pi over 2 to pi over 2, not from 0 to 2 pi, all right? Those are some examples for you. What is sine inverse of half? All right, already you know that pi over 3, I mean pi over 6 actually. So sine of 30, which is pi over 6, is a half. So therefore sine inverse of half would just be pi over 6. Similarly, you should be able to compute B. Now for cos, you all agree it's the same idea, right? Because it also fails the horizontal line test. If you draw a horizontal line, it's going to cut this graph at multiple points. Some of you guys are asking, how, let me draw that horizontal line. Look, you see I'm cutting at so many points, making it to fail the horizontal line test, meaning that it's not one-to-one. Now, how do we get inverse? Remember, the first step for us to be able to compute inverse is to make it one-to-one. This time, we cannot restrict it from minus pi over 2 to pi over 2. I will show you why. Look at minus pi over 2, look at pi over 2. You see, that is where that intersection happened the first way, where those two intersections happen. So we need to shift it, we need to use a different interval. This time, let's try 0 to pi. So if we cut from 0 to pi, there we go. It becomes a one-to-one, and we can be able to compute our inverse. So you see here, they're mentioning that for the cos function, you need to restrict it from 0 to pi for you to have an inverse. For the sine function, the tan function, you can use minus pi over 2 to pi over 2. But take note, for the tan, you don't include the minus pi over 2 and pi over 2, the endpoints. Why? Because at those points, you have an asymptote. All right. All right, we've already seen this. Those are the sketch with the domain and range. Guys, learn them. Know how to sketch this inverse function. And there is some last example there for you to go and enjoy them. The last two is fairly easy, right? Everyone can do this too. But the question now is how are you going to do this, right? I will show you what to do. The first step is let this whole thing, let tan inverse of x to be equals to theta, all right? If you let tan inverse to be theta, what does that mean? It means tan of theta will be equals to x. And your next step will be to try and compute a right angle triangle. What is tan of theta? You know that tan is opposite of adjacent. So if tan of theta is x, it means that you have x, and here you have 1. All right? And this is right angle. Pythagoras theory says that the hypotenuse is just going to be square root of 1 plus x squared. All right. And once you've established this, it becomes easy. Cos of tan inverse of x, because you've let tan inverse of x to be theta, it just becomes cos of theta. All right. So indirectly, you're computing cos of theta. All right. Why are you computing cos of theta? Because your first assumption was that let theta be tan inverse of x. Now, what is cos of theta from this? Is adjacent of hypotenuse. So you see your final answer is going to be 1 over square root 1 plus x squared, and you're done. All right. I hope everyone is happy with that. Any question? It's already past 6. Any question from your side? All right, someone said, are we going to write exam? If yes, let me just open it again. Are we going to write on campus or not? Okay, it's going to be online. All right. Yes, there's going to be an exam. We move into our traditional old system, which is 2 semester tests and an exam. All right. And for my course, it's going to be online. All right. I don't want you guys to come to campus. There's COVID restriction, so we're going to write online. Any other question before I let you go?
Sir?
I think I can hear someone talking.
Yes, sir. For the transformations, do you want us to just give you the final thing, or we have to show like sketch by sketch? Let's say half um 2 to the power x minus 1, like that. Do we have to now show 2 to the power x, and then we show the shrinking and also the vertical shift, like different
Nice
steps?
question. Very nice question. Do I want to see all the transformation? The answer is yes, because in my question, so you need to read my question. It depends on how I ask the question. In my question, if I say use transformation to sketch this function, what does that mean? It means I need to see all the transformation, all the steps. But if I say sketch this and then I put 1 mark or 2, obviously you don't need to show me the intermediate steps. But if I want to see the individual steps, I'm going to use the word transformation. Use transformation to sketch this function. Then you need to show me each of those from the primary graph all the way to the very last one. But the biggest mark is going to be for the very last sketch. All right. But I want to see that you've done something in between. You can't just draw the last graph and tell me that, look, I'm done. All right. You need to show me the transformation. All right. I'm just continue reading. On the learning guide, time allocated for classes is 4 to 6. May we please have class from that time so we have an interactive class and just going through lecture slide. Well, the idea of 4 to 6 was going to work if we were on campus. 4 to 6 is 2 hours of online lectures, which is a lot. Not everyone has that kind of data in the first place. And in addition, some people have other courses that go all the way to 5 o'clock. So hence, we just do 5 to 6. But like I said, if you have any question, make an appointment, send an email. We're going to discuss. All right. In terms of your marks, uh, if you wrote the quiz outside of Blackboard, like I said, I'm going to upload your marks, so you don't need to stress.